All right. So last week we covered the second half of the geologic structures. So we talked about the geologic maps. So we'll go ahead and get started with that review. And so remember that things on a geologic map, we have our units. So these are typically the bold fonts that are in these color-coded polygons. And those will tell us, based on the legends, what type of geologic unit we're referring to. Typically, they'll give a description in terms of age, also a description in terms of what type of rock material we're looking at. We'll have some additional symbols, such as these strike and dip symbols here, with a number referring to the dip angle. Strike, the long line of that strike is giving us the orientation, assuming that in this map north is up. And then the little tick mark is giving us the dip direction. We also have these solid lines and dashed lines that would give us indications of whether we're looking at a fault, a unit contact disconformity, etc., etc. All right, so we have bold line now highlighted in red. That's telling us that we have a fault. All right, so on a geologic map, like our topographic maps that we covered a couple of chapters prior, we have our north arrow. And generally, north is usually given with in an upwards direction. So north is typically up when you're looking at a map, unless otherwise noted. We have our scale. So we have a sense of physical measurable lateral distance on a map. And then we have our legend, which gives us explanations of the different symbols, line types, as well as the different units that are being shown on a geologic map. So structures on a map. In a previous week, we looked at the different types of geologic structures that we would commonly encounter, such as anticline, syncline, the types of folds that we would get, as well as tilt and of those sorts. So in a geologic map, when we're looking at folds, these will typically show up as repeating patterns in geologic beds. So remember, in a anticline syncline formation, we have repeating patterns that are repeating from the fold axis. So if we look here at the example map, we have these repeating patterns of green and blue. So this would just be a ribboning effect of in a compressional environment, where we have a series of anticlines and synclines that will combine together and create this nice little ribbon. And that structure, when shown in a geologic map, will create this kind of zebra stripe or tiger stripe pattern that we see here. We also looked at plunging anticlines or plunging synclines. And these will give us these U-shaped type structures, as we can see here in the example in the red box. Faults would be given with additional symbols. They would have sawtooth patterns for reverse faults, arrows that would indicate fault motion, or as well as up and down U and Ds that would indicate the direction of the fault movement. We'd also have unconformities, and sometimes these are marked with a symbol, sometimes they are not. And you can noticeably see these or determine these based on changes of the geologic material. So if we look back at where we have igneous rock and we have sedimentary rock directly laying on top of that, we have ourselves a disconformity. So we can look at our geologic map legend and determine our different geologic map units, and use those to determine where our disconformities are. If we have a sedimentary rock contacting directly on top of an igneous rock intrusion. So in our lab manuals, we also looked at some of the geologic map symbols. So these may not reflect the same symbols that we saw, Depending on your map maker and whatever standard that he or she chooses to follow, these symbols may vary slightly, but in a general sense, we always would have a strike and dip symbol, something that would indicate a anticline or syncline, faults, horizontal bed, vertical bed, so on and so forth, as well as sometimes some symbols that would reflect the different fault types. Here we have our normal faults that are given with a very specific up thrown block or down thrown block, with our dips, angle, and the normal fault symbol, as well as the reverse fault, which is shown with a sawtooth pattern um, bold line, where the sawtooth pattern is on the hanging wall block. And in a transform fault sense, where there is no vertical displacement, we have arrows that would give us an indication of the sense of motion, or the type of motion that we'd experience on this strike slip fault, which would give us the either right lateral or left lateral faults. So that is it for the review, and now we'll go ahead and move on to our current week's lecture, which is the earthquakes and the earth interior. So why do we care about earthquakes? For the obvious reason, earthquakes are highly destructive and they can create a lot of havoc on the economy. So this example that's shown here is the 1906 San Francisco earthquake. So this was a fairly large earthquake that started a fire in San Francisco, and that fire raged and essentially burned San Francisco to the ground. So in modern day now, we have a lot to lose with a large earthquake. We see examples of that from Japan, from Indonesia, and so forth. So we have here is two different stress models of Southern California, and the bottom left is showing kind of the Central California, focusing on the San Francisco region. And the bottom left is showing kind of the cutaway of the San Andreas Fault. So we're looking at the landlocked eastern portion, or eastern side of the San Andreas Fault. So we see stress accumulation here shown by color, and we see the year that is slowly climbing up on the upper right of the upper right model, and the next to the color bar on the lower left model. So these are different years, and we see stress accumulation as it grows brighter and hotter. So we have higher stress accumulation. When that warm color disappears, that would signify that that's when we had a large event, so a large earthquake. So this is type of data that was recorded and collected from historical data, paleoseismology, etc. And all of this was compiled into these models, where they would essentially tell us the timeline and story of how the San Andreas Fault would accumulate stress and instantaneously release that stress in the form of an earthquake. On the upper left, we see kind of a timeline of what the San Andreas Fault has gone through, where the San Andreas Fault is outlined in blue, and we have red faults that are scattered throughout the rest of California and Nevada. We see the different types of years and the sections of that fault that ruptured during those significant earthquakes. So earthquakes are recorded by seismometers, and from that we are able to produce seismograms. So the seismometer is a device to use to measure an earthquake, so to measure the movement, ground displacement, the acceleration, the velocity. And the seismogram or seismograph is a graph created by the seismometer. And it's a fairly simple weight type of machine, where it's commonly understood as a free hanging mass on a spring that doesn't move during intense ground shaking. So when the ground shakes, everything else except for the weight will move, and this is playing on top of one of our laws of physics, of inertia. Since the ground shaking comes by so quickly, that mass doesn't have a chance to move when everything else moves. So since that mass has a little pencil or some kind of a recording device on it, it records that earthquake on the spinning drum. And the record of the earthquake, we will see that we have an initial P wave pulse, and then we would have our S wave pulse, followed by our damaging surface waves. So the P wave pulse is the faster arriving primary wave. And this wave will arrive first. It's a compressional wave. And this is the type of wave that travels through solids and liquids. Following that would be our S waves. And these S waves would are our secondary waves. And these will move in a perpendicular pattern to our travel direction. And S waves are a shearing wave, which only travel through solids. So since we cannot shear liquids, it only travels through solids. Following that, we have our surface waves, which are the most damaging and slowest waves as well. But they have very high amplitudes, which means that they will be very damaging. So we have our P wave demonstration here, where we have our particle motion going in the same direction of propagation. And this compresses the particle, as we see by the little black square. And this is our P wave. So our S wave is one that has a particle motion perpendicular to the travel direction. So we see that in here it's an up-down direction. However, it can also be a side-to-side as well. So that would be our surface wave, or S wave, sorry. And for our surface waves, we have two different types. We have what's called a Love wave and a Rayleigh wave. So the surface wave is exactly as it sounds. It's a wave that travels along the surface. So the greatest amount of motion is at the surface, and as we increase in depth, we have a reduction in the type of motion, or the amount of motion. So we can see in the Love wave, it looks fairly similar to what we saw in the surface wave. However, we have the maximum amplitude of motion at the surface, and we have gradual reduction of that movement as we increase in depth. So having a clear understanding of these different types of waves and the velocity at which they travel and how they propagate, we're able to develop these early warning type systems. So for example, if we have a large earthquake, so for the 2014 Napa earthquake, that was a magnitude 6, we know that our P wave would arrive first, and we'd have our S wave that would arrive second, right? So we'd have our primary wave first, and then our secondary wave, followed by the damaging surface waves, given a large enough event. So with that, we are able to determine the lag time between the two. As we can see that our P wave will travel a lot quicker, and then we have our S wave. So given a greater enough distance, we can determine the temporal gap between the arrival of the two different waves. So if we're in, say, for example, Southern California, and we're looking at the Napa earthquake, we have our Southern California seismic network scattered throughout. So each of the green dots are these seismometers recording ground motion. So anybody with this shake alert, is what they call this program, will get an early warning. However, anybody who's too close to the epicenter, so the direct center of where that earthquake started, the P wave and S wave time gap between it will be too short, so an early warning system will not necessarily work for them. However, if we're further away, we're able to determine that we have significant shaking occurring within 5 seconds, within 4 seconds, within 3 seconds. And with multiple stations, we can look at the intensity of the shaking. So if shaking continues for several of the seismometers, then we start to ramp up the intensity of the shaking and a different type of warning. So it'll give us the weak, light, moderate, strong, very strong, severe, violent shaking levels. And this would be based on looking at several seismometers and the duration of the shaking. So a short duration of shaking will indicate a lower magnitude, also less shaking, but a longer duration of shaking usually will tend to be a more severe or violent, extreme type of shaking. So as you can see here in this model, as more seismometers are being affected, uh, they are recording not only the amount of shaking, but the duration of shaking. So based on that, now we're able to upgrade the amount of shaking, which initially started at a moderate to now moving into the strong category. And now in a being far enough from the epicenter, we're able to get a more longer early warning. So in this case, if we have the southern portion of the San Andreas Fault rupture, we have approximately 1 minute before those waves reach downtown Los Angeles, and that single minute is enough time to halt any major infrastructure operations that would cause a lot of damage if it was abruptly cut out. Or also give time to hospitals to, say, for example, stop surgery or have everyone exit out of a elevator shaft. So in this case, what should anyone do during a earthquake? Of course, they want to get away from any type of hazard or anything of that sort. Airplanes that are about to land should stay up in the air. Airplanes that are about to take off, maybe they should stay grounded or also take off to avoid the ground shaking. So this is the shake alert that was developed. And I believe that is also a current system that is being in play. And to learn more about this, you can go to shakealert.org or visit any of the affiliates that you see here, and they will also have information on Shake Alert. So that's very interesting and good, but now we need to go back and look at the very basics of our P wave, S wave. And now we need to locate an earthquake. So first, it's nice to have a nice system to give us a early warning system, but we need to know how that all works. So it works by using several seismometers, so minimum 3 locations, 3 seismometers, and through that we're able to triangulate the location of the earthquake, so the epicenter of that earthquake. And we do that based on the lag time of the P wave and S wave. So that same lag time that was used for the early warning system is also used for locating precisely where that earthquake is coming from. So if we look here at location A, B, and C, we see that the lag time for location C is the longest out of the 3, being A with the shortest time. We're able to determine that, for example, location A, the lag time between P and S wave is about 1 minute. And for B, we're looking at about 2 minutes. And for C, we're looking at about 3 minutes. So, based on a P-S wave travel time curve, we're able to determine precisely where that earthquake is coming from. And we do that by looking at this, the gap time between our compressional wave and our shear wave, which is our compressional wave, remember, is our P wave, our primary wave, and our shear wave is our S wave. So we measure that distance between the graph, between the two curves, and we compare that with the time axis on the y-axis to determine where that 1 minute gap is, where that 2 minute, 3 minute gap is. So from that P-S wave curve, we can determine a distance from A, B, and C location based on the time gap of 1 minute, 2 minutes, 3 minutes. So with that, we're able to now draw circles. And where those 3 circles will intersect will give us our earthquake epicenter. So that is the earthquakes portion. Now we'll move into our Earth's interior, or the kind of more of a plate tectonics review. So knowing that we have earthquakes that occur along the plate boundary, and on these plate boundaries we have 3 different types of plate boundaries. We have our divergent, convergent, and transform type plate boundaries. So remember that our divergent boundaries is our ocean spreading centers, where we have magma upwelling that splits open the crust and that pushes and creates new crust. In our convergent type boundary, we have crust that is being collided with another type of crust. The common textbook example is an oceanic and continental crust, where the oceanic crust will be subducted underneath the continental crust. And this contact point between the two creates an intense amount of friction and stress, and that is released in the form of a very large earthquake. Now we also have the example of transform fault, where we have 2 blocks that are sliding against one another along a fault plane, and this is also known as a strike-slip fault. So all of this occurs on the upper portion of the Earth, so the Earth's crust, but there is much more of the Earth than that. We also have the asthenosphere, the mantle, the outer core, and the intercore as well. So as you can see from our image here, we have a significant portion of the Earth that we have not yet covered. So that brings us down to the different melting temperatures. If you can recall from the igneous rocks lab, we had the Bowen's reaction series, where it gave us different melting points and temperatures for specific mineral types and when they will melt and solidify and crystallize out. We had several exercise questions regarding that. And it's pretty similar here as well, where we have the dashed line giving us the melting curve of dry peridotite. So as we have our crust in the upper 50 kilometers, and this is our, for the most part, solid Earth, or solid crust. And as we gain depth, we increase our heat and pressure, which essentially will translate to a molten mantle state, all the way down to the Earth's core, or inner core. So with all of that said, I want to remind everyone that is in our 1104 lab at OU that we have an upcoming final, and the current information for the final exam will be uploaded to Canvas.